Hello everyone and welcome to another edition of Nanotalks. This Nanotalk is a recording of a webinar, our very first Lightning user webinar we did with Dr. Martien den Hertog, and she will be presenting her work on semiconducting nanowires using in situ biasing and heating. So now we will switch to the recording. You will first hear me introduce her to the audience and then she will start her presentation. After our presentation, as always, we have a Q&A with the audience. So I hope you enjoy this Nano Talk.
And of course, the biggest welcome is to our presenter today, Martien den Hertog. Martien studied chemistry at the University of Utrecht in the Netherlands from 2000 to 2005 with a master entitled Chemistry and Physics. She performed her PhD then in France at the CEA Grenoble from 2006 to 2009 under the supervision of Jean-Luc Rouvière, entitled Characterization of Silicon Nanowires by Electron Transmission Microscopy. So that's when her journey into transmission electron microscopy started, I guess. She performed her postdoctoral research on TEM of 2 to 6 nanowires at CNRS Institute Nil in Grenoble, where she is now a permanent research scientist since 2010. She has been our first Lightning customer, and she's been using the dense 6-contact double tilt Lightning system since 2013. So she's not only our first customer, but also the first person to give a Lightning user webinar on our platform. So we're very happy for that, and we welcome Dr. Martien. So that was my introduction. Now I want to give the floor to Martien, and I will change the presenter mode, and then I hope you enjoy her presentation. So go ahead, Martien.
Hi, everybody. So let me just go to full screen. Oh, sorry. Okay, so I hope it is fine. So welcome. I'm Martien den Hertog. Thank you, Olaf, for the kind introduction. So it's a great pleasure to present you my work on in situ biasing and heating of semiconducting nanowires. Lots of people have contributed to these studies, mostly in the Grenoble area, but also in the Paris region and at Technical University of Vienna. So because I cannot see you and I don't know from what backgrounds you come, I wanted to start with a very basic introduction. So I will speak a lot about nanowires, more in particular semiconducting nanowires. And basically, we can make these structures in two different ways. So one potential method of making them is by so-called bottom-up growth methods. So these are often catalyzed. For example, we can use a gold colloid on a substrate and then either supply the atoms from which we want to build the wire in a gas using a precursor, or we can use a molecular beam, like in molecular beam epitaxy. And these atoms are then supposed to go into the catalyst particle. And when the supersaturation is reached, we can grow these pillar-like structures. We have a second option to make such nanowires, and this is by so-called top-down fabrication. Using lithography and etching methods. So very briefly, you spin a resist on your substrate, and then you use some radiation, for example, photons or electrons, and you expose the resist in some regions, but not everywhere, with the idea to transfer a pattern into your resist. And the resist is then modified, and this allows you in a development step to locally remove the resist, either at exposed or unexposed locations. And then if you put, for example, a metal, and you can do a final lift-off step to remove the resist, the metal only remains where it's on the substrate. Then if you do any isotropic etching, you can etch, and this metal acts then as a mask, and you obtain similarly these pillar-like structures. So nanowires have great potential for many different applications, ranging from photodetectors to field effect transistors, light-emitting diodes, and solar cells. I just showed you these two possibilities to fabricate the nanowires, and at this moment, the nanowires made by top-down fabrication are much more advanced into devices. So they're in fact everywhere, in the phone and in your PC. However, in this talk, I will mostly speak about nanowires grown using bottom-up methods, and this is basically because they are slightly more easy model system to do this kind of experiments. So basically, nanowires are really interesting and have a high potential. However, some challenges remain. And first challenge is a variability issue. So with today's state-of-the-art growth and synthesis methods, we can have the problem that each nanowire can be slightly different, while they should be, of course, nominally identical. And to shed light into this issue, it can be very interesting to do a structure properties correlation at the level of the same single nanowire. For all these applications, we also need electrical contacts to the nanowire. So it's very important to allow fabricating them and controlling them. And TEM with its atomic spatial resolution is a great tool to look in high detail at these contacts. And of course, if we can make a contact using in situ TEM, we can also understand better how all these diffusion processes occur. Last challenge is related to internal electrostatic potential. So in most devices, we need some varying potential landscape, for example, a p-n junction where you have doping contrast, and this can then be also influenced by surface charges or charge traps. And so therefore, it's highly relevant to study electrostatic potential at nanometer length scales to truly understand why the device behaves as it does. So I'd like to address parts of these three challenges in my talk today. So this brings me to the outline of my talk. First, I will rapidly explain to you the sample fabrication and the transmission electron microscopy technique that was used. Then I will first show an example of a correlated study on gallium nitride, aluminum nitride nanowire heterostructures. In the second part, I'll show you how we make aluminium contacts on germanium nanowires using in situ metal propagation. And this is the first in situ part, in fact, in situ heating, basically. And finally, I'll show you the study of a Schottky contact on a zinc oxide nanowire using the combination of in situ biasing and electron holography. So the working horse of my research is basically this kind of sample that allows you to do a multitude of different experiments. So we find a silicon nitride membrane, preferably with a hole, where we can suspend a nanowire, and then we can put electrical contacts on these nanowires. And we can hit these structures, for example, with photons or electrons, and characterize different signals that are coming out, for example, photoluminescence. And all signals can also be combined with electron transport. And additionally, we can combine all these techniques with characterization of the same object based on transmission electron microscopy. For example, to look at the chemistry of the structure or the crystallography, like defects. And additionally, we can use these contacts to do in situ TEM experiments. So this is a very nice sample structure that allows you to do many things. So then with this sample structure, we can easily correlate different experiments on the same objects. We can heat the contacts in situ and improve the contact and study the reaction, and use these contacts to measure electrical properties in TEM. So now the question, before going any further, how can we make a sample for electrical in situ TEM? So how can we make this sample? Basically, there are two possibilities. One option is to use lithography-based methods. So I've shown you in the second slide how lithography basically works. This approach has advantages. For example, this is a method that typically will give you good electrical contacts. This is also the method of choice used in groups working on electron transport, and also in industry. And it's possible to contact many structures in one batch. There's also drawbacks because TM samples tend to be rather tiny, and it's a bit more challenging to do this on these tiny samples because you have to often put them in many different places and in solution. So then you can easily break these fragile silicon nitride membranes. And also this is like an ex situ technique. You do not have direct feedback how your lithography is turning out. Another option is to use the focused ion beam. Using this technique, it is probably more difficult to get high contact quality. With development, this can maybe be optimized, but it is for sure that in real devices, contacts are not made with a focused ion beam. So you will need always some trick to be sure that you're studying a contact or not being influenced by the contact of the FIB. It's a technique that's very well suited for one sample at a time, and also this is an advantage because this technique is very well suited for one-of-a-kind samples. This is a microscopy technique, so it's an in situ fabrication method, and I think that for this reason this approach is mostly used by microscopists. It comes also with other disadvantages. Because you have this highly energetic ion beam, you may risk to damage or modify your sample. This is related with potential surface amorphization or redeposition. So both techniques has its advantages and disadvantages, and it really depends on what you want to do, what is best. What I will show you today is based on lithography. So when I started this activity in 2010 in my institute, Institute NEO, in the clean room nano fab, they already mastered fabricating these silicon nitride membranes. Since then, we have optimized their fabrication for correlated and in situ TEM experiments. So we fabricate these membranes on the 4-inch wafer scale. So there are many, many membranes on one wafer. And then the membranes are organized in groups. So we have arrays of membranes. For example, here you see part of such an array. And this helps us a lot to do the lithography because we can work on larger substrates and we can contact several nanowire, each on a different membrane in one run. So on these membranes, we disperse the nanowire and then they're contacted with electron beam lithography. On the back side of the chip, we have these cleaving lines, and so when we are all happy with fabrication, we can push here on the front side and cleave out a single chip, and this we then put in into our 6-contact double-tailed lightning holder, where we have these 6 needles landing on the big contact pads to make the connection between our nanowire here and the outside world. So if you're interested in this, the fabrication of these membranes, we recently did this review paper. It's nanotechnology that will be out very, very soon. And here there's much more details about membrane fabrication and also a review of all the studies we did with this kind of sample structure. So few words about the electron microscopy. In the first 2 parts of the talk, I will mainly speak about scanning transmission electron microscopy. So here we have a focused electron beam that is scanning over our sample point by point. And at each point of the scan, we can collect the intensity, for example, on a bright field detector, or we can collect electrons scattered over larger angles on a so-called high angle annular dark field detector. And this is quite interesting because this kind of images are sensitive to the atomic number Z, so it's relatively easy to get a qualitative chemical contrast. And this work was mainly performed on Titan microscopes that are present in CEA, in the ERIC department, in the Lemma group, within the nano characterization platform. So the first study I'd like to show you today is a correlated study on gallium nitride, aluminum nitride nanowire heterostructures. And here there is we had a particular interest in the polarity. So first need to explain this to you. These nitride materials, they crystallize in the wurtzite crystal structure. And because in this structure we have no centrosymmetry, we have lots of little dipoles here between nitrogen and gallium columns. In the crystal, each dipole is compensated, but at an interface, the dipole may not be compensated. For example, if we grow first gallium nitride, aluminum nitride, and again gallium nitride, at the interfaces we find uncompensated dipoles. So depending on the polarity, we get a sheet of fixed charge with either negative or positive charges. So you get this very strong bending of your bands and very strong internal polarization field. So this has a very strong effect of electric properties. So this is the study we did. So here we have a gallium nitride nanowire with a single aluminum nitride insertion. And if we look very high resolution, this is an averaged high angle annular dark field stem image. We see here these bright dots that are the gallium columns, but we can't directly see the nitrogen columns because they are much lighter. But if we make a line profile along this line here, we see here a little bump, but here is a dip in the contrast. And so this analysis allows us to place the nitrogen atoms in the lattice, and this shows that the C plane here is terminated by nitrogen, and this is what we typically refer to as a 0, 0, 0, -1 n-polar nanowire growth direction, because the nanowire grows to the left on my screen. And this was also confirmed by annular bright field stem. So maybe more interestingly, we could also correlate this polarity to the electrical properties of the nanowire. So you can see that this nanowire has electrical contacts. And I already told you it has a single aluminum barrier that you can see here. It's a darker contrast. And aluminum nitride is wide band gap, so it's basically like wood. Electrons don't like to travel through it. But there is a shell of gallium nitride around the aluminum nitride barrier, so current very likely flows in the shell. If we do a simulation of the conduction band profile in the shell, due to the combined effects of strain and polarization fields, this looks very much like a p-n junction. And this p-n junction-like conduction band explains that if we do a current voltage measurement of this nanowire, we get this diode-like behavior with a higher forward current for a positive forward bias. So it was coherent, the polarity and the electrical properties. This was published in these nanoletter papers. So to summarize this first part, I showed you that nanowires grow in the n-polar 0, 0, 0, -1 direction. We can clearly observe the influence of the polarity on the properties of the nanowires. We had these 2 papers about this, and the properties of contacted nanowires are much easier to understand if you do correlated TEM, and you can check if you're interested also this other publication. So this brings me to the second part of my talk. Here actually the in situ part starts. So we have looked at making aluminium contacts on germanium nanowires using in situ metal propagation. We looked at the reaction, the chemical composition, the kinetics of the reaction, and finally show you that we can fabricate in this way very small quantum disk structures. So this work was carried out mostly in the PhD of Khalil and more recently Min An Yuan. In literature, it was clearly recognized that this kind of metal entering a nanowire is very interesting and very promising, because if the metal enters the nanowire and we can control this remaining semiconductor region, we can fabricate such a very small semiconductor channel with very abrupt and well-defined interfaces with this metallic or metal contact. So we can find a lot of papers on nickel in silicon, for example, this paper by Wu, also this paper by Tang. Also, other material combinations were studied. The focus is on silicon, but here, for example, platina in silicon, and here also study of indium propagating in zinc oxide. This is the next point I have to explain to you. So we have done also heating studies. So in most of the experiments in literature, more conventional approach is used where a heating holder is used, heating the entire tip of the sample. We have looked at the metal propagation in germanium nanowires using Joule heating. One approach is to use this dense solutions heater chip. So this is an image of a dense solution heater chip. Here on the membrane you find this metal spiral. You have two contacts to drive the current and two to measure the potential. Here you see a close-up of the chip, and in between the spiral you have these little windows that can either be a thin silicon nitride membrane or a hole. So we use the ones with thin silicon nitride. We disperse the nanowires, and then with the electron beam lithography put metal on top of the nanowire. So it's not a true electrical contact because we didn't combine this with electrical biasing, but just provide the metal reservoir. The advantage of this approach is that these chips are well calibrated in temperature. So this is very nice. The second approach we used was patterning structures on our homemade membrane chips, for example, structures that you see here. And then on the membrane, we had also dispersed the nanowire and contacted by these kind of metal strip lines, each going to their own contact path. And if we flow a current through such a strip line, we have a very, very local Joule heating that can start similarly a solid state reaction. The advantage of this approach is that it is more easy to combine with electrical biasing, and it's more easy to make a contact very many nanowires in parallel. The drawback is that these homemade nano heaters are not temperature calibrated. And I should add that this idea was published in this ACS Nano paper. So now I would like to show you some first experimental results. So here you see two germanium nanowires side by side underneath a aluminium strip line. And then we flow a current through this strip line, heating up the system. And you will see that we see a contrast change in the nanowire. So this is high angle and another dark field. And the germanium nanowire has quite a bright contrast. It's quite heavy. And this is then progressively replaced by a more darker contrast, likely related to a lot of aluminium, which is a lighter element. So you can see that once all the material underneath the strip is consumed, the interfaces progressively extend out into the nanowires symmetrically with respect to the heating strip. And you can also see that these interfaces are very, very abrupt and well defined. So this system was first observed by the colleagues in Austria. There's a nanoletter paper by Kohl. And since then, we have done a lot of in situ TM experiments on the system. So one of the first things that we wanted to look at was the chemical composition of the created segment. So we used energy dispersive X-ray spectroscopy. Here you see an EDX map. Oops. This is the converted region, and then we made a profile that we integrated along the nanowire to increase the signal-to-noise ratio. This profile was then quantified using the zeta vector method, and we compared it with 3D model calculations. And the reason we can do this is that the cross-section of the nanowire has a certain symmetry, and in this case, the cross-section had an hexagonal symmetry. So then we can calculate an expected profile for a certain combination of hexagons and see how well they fit with the experimental data. This method is first published in this paper by Argueda. So using this approach, we saw that the core of the converted region was pure aluminium. It was surrounded by a shell of aluminium oxide, and on both sides of this shell we had a thin layer containing almost pure germanium. We also observed, and I don't show it here, that this aluminium nanowire we create is monocrystalline. So in fact, we create this core shell structure, the core of pure aluminium. Another thing we looked at was the reaction kinetics. So we followed the reaction interface position, and here I show you results on nanowires with small diameters. This is an experiment done by the very local Joule heating, so not calibrated in temperature. So you see L, the distance the interface has traveled as a function of time. Here you see an experiment carried out at 250 degrees on the dense chip. And again, the distance the interface has traveled as a function of time. So these kind of curves, we're always showing this kind of parabolic behavior, and we could fit them very well with this relation. That's a classic diffusion equation where the length the interface has traveled can be related to the square root of the diffusion constant and time. And this fact indicates that the reaction is limited by the diffusion process. Now, in literature, we can find models about how this curve should look in the case of what limiting the reaction. And for this system, we saw that the speed of the interface progression can be different according to the nanowire diameter. For example, here the smaller one goes a bit faster, but it's not systematically the smaller one going faster. Here you see that the fastest one is the intermediate diameter, the red one here. And so this indicates that if the smaller one is faster, it's likely that it's a surface effect. But since we don't clearly observe this, we think that the reaction is limited by some bulk diffusion effect. So it is likely to be the diffusion of aluminium to the reaction interface. We have also looked at the reaction kinetics, checking the interface position in nanowires with much larger diameters. So here the diameter is around 127 or 150 nanometers. So this is again an experiment where you see two nanowires side by side underneath the aluminium heating strip. And following the position of the reaction interface over time, we see that now we get this more linear relation, and they basically proceed at the same speed. And according to models, this may indicate that the reaction is limited by an interface. So another thing we observed in nanowires with relatively large diameter, so above 100 nanometers, is that the interface can progress in jumps. So I will show you this video. This nanowire was just as grown, so on the surface there will be some native germanium oxide. And you see that up the interface can jump, and then it flows over, the step flows over the interface region. And here we have some roughness at the surface, and this is correlates with a much larger jump of the interface. So there it goes again. And it's very clear that if you want to make a semiconducting region very well defined and controlled size, these jumps should be avoided, because you want to make your 1, 2, 3 layer and poof, jump, gone. So we needed more control. And one thing that Min An did was to passivate the surface. So he put, using atomic layer deposition, an aluminium oxide shell on the nanowire surface. And this indeed helped a lot to get a much smoother propagation. So here you see an experiment where the aluminium was already propagated from this side, and then the heating is performed on this side of the structure. And you can see that now the interface is much more well behaved and smoothly propagates into the nanowire. And finally, Min An, he succeeded to make a germanium quantum disk of only 7 nanometers, which is among the smallest reported in literature. Of course, this is basically a proof of principle experiment. I think it's really super nice. So, summary of the second part. In thin nanowires, we observe that the reaction is limited by aluminium volume diffusion, as there is no clear size dependence of the reaction kinetics. In thick nanowires, the reaction appears limited by the reaction interface, and interface can remain trapped at the surface. So this is likely related with roughness or surface defects. We see that aluminium and germanium diffuse in opposite directions, and germanium is diffusing back to the aluminium reservoir, likely by surface diffusion. So we think that here you have the interface, aluminium is coming in through the volume, and then germanium is going into the surface channel where it was detected by EDX, and going back into the aluminium reservoir where we have also detected it by EDX, but I did not show you these data. Then finally, surface passivation improves the control of the interface, allowing you to deterministically fabricate small quantum dots or quantum disks. So if you're interested, here are the 2 publications we did about the system. So now coming to the last part of my talk, in situ biasing and holography. So first I would like to explain rapidly what off-axis electron holography is. So for this technique, it's TEM technique. We have a parallel beam, and the sample is put in part of the beam. The other part of the beam goes through vacuum. Then, with the help of a charged wire called the biprism, we interfere these both waves to obtain an interference pattern or hologram in the image plane. The big advantage of this technique is that from the hologram you can calculate, you can reconstruct both amplitude and phase images. And in normal TEM, you only obtain the amplitude image. You lose the phase. It can be very interesting to have these phase images because the phase, the change in phase, is directly related to magnetic properties, but I will not discuss this, but also in the absence of magnetic fields to the projected electrostatic potential. So you integrate along the sample thickness, and there you find this potential term, and you only need to multiply with this constant. The problem of electron holography, but of course it's like super nice, you can measure electric properties at nanometer length scales, but of course there's challenges, is that it is difficult to do this in a quantitative way because you can have other influences on the phase change, for example, chemical contrast. We can tentatively separate this potential term into a contribution of the chemistry of the sample, the atoms, because they will dephase your electron wave. This is typically referred to as main inner potential. And on top of that, we have basically the real electrostatic potential term related to things like doping and surface charge and Schottky contacts and so on. Another problem is that there can be other influences on the phase. For example, diffraction contrast. If your electron is diffracted many times, this will also change its phase. Then finally, not the entire sample thickness is necessarily electrically active, but you will integrate along the sample thickness, so you need to know the thickness because you can have surface depletion or inactive layers. So the solution to this problem is to use in situ biasing, and then you can subtract the reference image, typically a 0-volt image, and remove all signal but the varying potential. And this was already a long time ago, this was clearly recognized in literature. So here I show you the state of the art in situ biasing and electron holography. You can find several papers studying p-n junctions in bulk samples, here by Fazzini and also by Twitchett. And in nanowires, attempts were made of in situ biasing on p-n junctions, here with an approach like a nanofactory to make the contact. And in this paper, they succeeded in measuring the resistivity of the nanowire using in situ biasing. So it's clearly very interesting. Now we've tried to apply this to a Schottky contact. So I wanted to remind you briefly what a Schottky contact is. So we have a metal and a semiconductor, and when you bring them into contact, there's 2 conditions that need to be fulfilled. The Fermi levels must line up and the vacuum must remain continuous. And this forces then the conduction and valence bands to bend up or down at this interface, and therefore you create this region next to the interface that is void of any mobile charges. So this is the depletion region. Then if you increase reverse bias, you increase this depleted region where you only have fixed charges. And this is basically what we want to visualize in the study using electron holography. So we started this work because my colleagues, Fabrice and Julien, they had done many cathodoluminescence experiments in SEM on these zinc oxide nanowires. And in short, the depletion length extension under bias was not so well understood. So here you see the sample we also studied for TM, but this was also characterized by cathodoluminescence. Here's the hole in the nitride, the contact that we will bias, and then the wire is contacted to the contact to ground through these crossing nanowires. So here's the STM image, and then you have a CL map at 0 bias. So the black contrast means that light is emitted. Then if we apply negative bias to this contact, we are progressing the depletion with inside the wire. And then if here you hit the wire with your electron beam, you create still an electron hole pair, but now there's a field because you have a depletion region. So your electron hole pair, they're separate and they can't recombine radiatively. So here the light contrast means no light. From a profile in this kind of maps, like here, you can then extract the depletion length as a function of bias, and you always find this linear relation with depletion width as a function of bias. And this is difficult to understand because from bulk equations or finite element simulations, we expect a square root extension and not a linear relation. So this is why we thought, well, let's try holography, what we will see. So here you see the TM image of the same nanowire, and here you see a hologram, and we worked at 80 kilovolt to avoid electrical modification of the sample. So we took series of holograms. They were then each all corrected for drift. An average phase image was reconstructed, and from this average phase at each bias, we subtracted the 0 bias phase to throw away all the contrast not related to electrical phenomena, right? So here you see just examples for this 0 bias corrected phase image, for example, at -10 volts, and this is a 0 bias difference image of the difference between 0 bias images made at different moments to be sure that the object is not being modified over time. So we varied the bias from 0 to -15 volts. And then here I show you phase profiles from the contact going into the nanowire. This is these profiles here. And you can see that for a decreasing bias, the phase is going down more and more and penetrating further and further into the nanowire. So what you see here is in fact the depletion region penetrating further and further into the nanowire. So I think that's really nice. From these profiles, we can then extract the depletion length. And the next step is that we want to compare these depletion lengths with a simulated depletion length. So we have performed 3D next nano finite element potential simulations, playing with different n-doping concentrations because it was known the wires would be unintentionally n-doped, and also putting different values of negative surface charge. So here is a comparison of experiment and simulation. Here you see the square of the depletion length, and here is the negative applied potential. These black symbols are the experimental data obtained from the holography experiment, and they are fitted by this equation that expresses the depletion width in a bulk system. So you can see that in a nanowire, in fact, the extension of the depletion length behaves like a bulk system. So you can see that these green symbols, the colored symbols, are different sets of simulations with different doping and surface charge. These green symbols, they resemble the experimental results relatively well. And this would indicate a doping concentration around in the order of 10 to the 18 and a negative surface charge of around -2.5, 10 to the 12. But since the depletion length depends both on doping and on surface charge, this is not a unique solution, but it does so happen that these values agree well with other independent measurements of these values. Another thing that is interesting to look at is to compare the depletion width measured with holography with the depletion width obtained. This is on the same object measured with SEM cathodoluminescence. The red curve here. So here the depletion width is in linear scale. So for the holography, we see that we have really this kind of square root behavior, but the extension of the depletion length measured with cathodoluminescence really follows this linear trend. And we can explain this saying that in holography, holography is more sensitive to the nanowire core, while SEM techniques are more surface sensitive. But it is still difficult to comprehend that we get different results even on the same object. So to summarize this third part, the doping of the nanowire is estimated in the order of 10 to the 18 atoms per centimeter cube, and this is compatible with the metallic nanowire like we had previously published. Surface charge in the order of minus 2.5 10 to the 12 charges per centimeter square, compatible with this publication in nanotechnology. And on this wire, it gives us a depleted surface region in around 36 nanometers and an active thickness of around 70 to 80 nanometers. So the active thickness agreed very well with the strength of the phase signal we observed. And this depleted surface region agreed very well with optical measurements in this paper. This was published in this nanotechnology paper. So finally, I would like to thank all my collaborators, in particular all the PhD students that did great work. Khalil, especially Min An Luong, Maria Spies and Akil Ajay. Would like to thank the research facilities, the Institut Neel of CNRS, so that is here on the map. Here's Grenoble, by the way, France. This is Grenoble, it's very nice, we have lots of mountains. Here is a group in CEA that works a lot on nanowires, 3.5s and nitrides and 2.6. And I also collaborate a lot with this group in Minatech, where we have the nano characterization platform and benefiting of this great equipment for TM. So I showed you 3 topics: correlated experiments, the aluminium exchange reaction in germanium nanowires, and the possibility to visualize the depletion width using electron holography. So I think that in situ TEM is quite a powerful tool. I would like to thank also the funding agencies, the ANR, the local networks, and more recently the ERC that allow me to do all these great and interesting experiments. I would like to thank you for your attention, and I hope you have questions later. And if you have them at a later moment, don't hesitate to reach out and contact me. Finally, okay, I know that most of you are in the States, but in Europe, we are organizing a very interesting school, Quantitative Electron Microscopy 2021, and this is a 2-week event. Basically, everybody in the TEM field will be there, and also lots of constructors and also in situ holders. It's really super nice. So don't hesitate to check the website and join us in May in France. So thank you for your attention, and I'm open for questions.
So before we go over to the questions, and I invite everybody again to share any question you still have. I would like to ask you, Martien, as our customer now already for 7 years, using the lighting system and having a lot of contact also with the people at our company. Can you share some of your experiences with the system and with us as a company?
Yeah, so I remember very well. Basically, I was so I started this membrane activity in 2010, and first I was using another system but it was quite difficult to use. And so I think it was in Manchester in 2012, I first discussed with Ben Bormans, and so then, well, this was really seemed like a so much easier solution to make the contact with these needles, and it was always very yeah, I've always really appreciated the contact with then solutions, because I had the first prototype. So in the beginning we had some small problems. They were always very reactive and fast feedback, and really helping me to do these experiments. So I had a very good and still now when I have problems, it's still very reactive. So I have a very good experience with the dense solutions team.
All right. Okay. Well, that's great to hear. Thank you very much for that. And we can now go to the questions. I had one question from Ariel Petruk. So the first question was, what was the heater chip used on slide 21?
That's me. I did not number the slides. Sorry. No, the slide 21 is our homemade chip. And in fact, you can, well, kind of know it, because we, this is like, we often refer to it in papers as direct Joule heating, because the current is really on the sample. So it's super local. It's more local than the heating on the dense chip, because let me go back in this slide. For the dense chip, you have this spiral. So this whole part here in the center is heated, while in this what we call local direct Joule heating, you mostly heat this part of the strip. So this experiment is not calibrated in temperature, but by chance we had these two nanowires side by side, and this then is still interesting because it, as the two nanowires, we don't know the temperature, we can just compare them the one with the other. So it still gives us some information about kinetics and potential influence of the nanowire diameter.
All right. And there was another question. How long are the jumps in slide 26?
Yeah, I think I know this. Yeah, so they can be really, in this slide, I think they are like, okay, you can see that the width of the nanowire is 130 nanometers. So they can be even up to 10 nanometers. Sometimes we have seen that the propagation is difficult to start, and then we heat it more, and then you can get even bigger jumps. But I guess that this is kind of related to some defect at the metal nanowire interface, additional defects. But these jumps can be pretty big, like at least 10 nanometers.
All right. And Dan, my colleague Dan Zhu, she asks, is there any influence of the sample thickness to holography results?
Yeah, it's the sample thickness, huh? Not the membrane thickness. Yeah, definitely, because sorry about this. So if your phase signal is directly proportional to the thickness of your sample. I mean, here we write an integral because you integrate, but if you don't have any changes in your potential, you can just write it as your delta potential times your thickness, basically. So yes, there is definitely an influence. So the thicker your object, the more signal you will get, until your electrons cannot traverse anymore, because then you get nothing. So it's yeah, there's an optimal thickness, and in silicon you can easily work with 100, 200, even thick nanometers thickness, and then it depends on your material. If you put more heavy atoms, you will have to make it thinner, basically. Because
right, so
yeah, I just wanted to add that the electrons you're interfering they have not undergone any scattering. They are coherent. So if your sample becomes very, I mean, maybe a very thick sample can still work if you're doing EDX or EELS, because you're looking at electrons that have undergone a scattering event. But in holography, you're looking at electrons that have not undergone any scattering event.
All right, so I hope that answers our question. Here are the questions coming in. Great. Okay, thank you. So we have the first question from Sardar Bilal Alam. He first thanks you for the talk, and his question is on the mechanism of diffusion in the aluminium germanium system. Can you please comment on thermal and electromigration in these systems, and what direction aluminium and germanium follow?
Yeah, it's a very interesting question. Okay, so thermal and electrical migration. So what we have seen is, if we use, this is the aluminum strip, right? If we use this as a local heater, we have a current flowing through it, and this can damage the strip because of electromigration. In fact, at some point in history, aluminium was used in interconnects as the contact material, and they stopped doing that because of these problems of electromigration. So this is limiting also the temperature you can reach with this lithographically defined aluminium strip. But it's not really influencing your reaction, in the sense that okay, you cannot do the reaction anymore if the strip is damaged. But yeah, it's rather like an experimental problem. And sometimes if you are creating, or you can see that your strip starts to damage, what you do is you reverse the current direction, and then you can sometimes heal these problems. In the aluminium germanium system, we didn't really see a big influence on how we do the heating. If we do this heating with a local heater, or if we do the heating like here with a dense chip, we did not really see a difference. But if we did these experiments with copper on germanium nanowires, I have not shown any of these results, but we have a paper. Then we did see that the reaction appeared to start slightly easier when we have the current in the strip. So the current in the strip may help to start to have the first nucleation, to start the reaction. But it's not super clear. And at least we did not see this for the aluminium germanium system. And it's true also that we haven't put particular effort into calibrating the temperature in our homemade chips. So what we know is that we just put a potential on the strip, then we get the current, and we see at some current the reaction starts. But this is not very reproducible. And this is basically the big advantage of these calibrated chips, that it's plug and play basically. Now, it is possible to use TM-based methods to measure the temperature. And we have done some first experiments, but this is a whole other development that for the moment we didn't really go into. So if you could measure the temperature in this local heater strip with the TEM, then it would be easier to give I could give a more detailed answer to this question. So for the moment, the effect is mostly the heating is starting the reaction. It's not so much effect of the electrical current. Is it answering your question?
Yes, it definitely answered the question. So
Great.
we have one last question before we go to the closing words. And the question is from Alexander Kristal. And he thanks you also, or she, I never know with these names, international names. Thank you for the presentation. I'm wondering about the interface reaction between aluminium and germanium. What was the temperature of the reaction, and what is the driving force for it? So maybe it was already
Yeah, this is an interesting question that has been raised before. So the temperature of the reaction is, so here, I hope you can see my mouse. This experiment was like the lowest temperature where we started the reaction. It's 250 degrees. Typically, the temperature, the reaction would start around 300, 350 degrees. Sometimes we also saw that it would not start and then would go to much higher temperatures. And then if it starts, the behavior is different, that it really, the interface advances in huge steps. So this was about the temperature. Second part of the question was, what was the temperature?
The second part was, what is the driving force for it,
Yeah,
and why
exactly.
aluminium replaces germanium in the nanowire?
Yes. So what we think is that the driving force is that the germanium can lower its energy by going into this aluminium strip, sitting at surfaces and grain boundaries. And apparently, if you supply this heat, it's more energetically favorable for the aluminium to go in, and then germanium can lower its energy by going into the strip. And we cannot reverse the reaction. Yeah, so this must be the driving force.
All right. Thank you, Martien. Wish you a very nice day, and thank you everybody for watching, and I'll see you at the next webinar.
Thanks.
Bye.
And that brings us to the end of this Nano Talk. To stay informed about upcoming webinars, I invite you to follow our social media channels, LinkedIn and Twitter. I also invite you to sign up for our monthly newsletter, in which we share interesting in situ research and technological innovations. I want to thank you for watching and hope to meet you at one of our next webinars.